All right, hello. Welcome again to C++ programming. We are on page 341 in our textbook, and we'll be discussing pointer variables. Pointers, one of C++'s most powerful yet challenging to use capabilities. Pointers enable pass by reference and can be used to create and manipulate dynamic data structures, which can grow or shrink during program execution. This is very exciting. This chapter shows the intimate relationship among built-in arrays and pointers, and lets us know that C++ actually offers two types of strings. String class objects, which we've already made use of, and then the C style pointer-based strings, which is actually inherited from older legacy C language. Chapter 6 introduced references that can be used to pass by reference. Now in review, with pass by reference, the caller gives the called function the ability to access the caller's data directly and to modify it if the called program chooses to do so. So it's actually referencing back to the past parameter, and you are able to modify or change, reassign the caller environment's variable. A reference parameter is an alias for its corresponding argument in the function call. To indicate that a function parameter is a pass by reference, we followed the param in the function prototype and header with an ampersand. And remember that all operations performed on a reference are actually being performed on the original variable. On line 7 in chapter 6, page 243, we have figure 6.17 C++ program. Again, in review, the function prototype is indicating that this function will not return a value, but square by reference is expecting that a reference argument be sent to it. And it indicates that in the function prototype with the data type immediately followed by the ampersand. In line 33 of figure 6.17 on page 243, square by reference is being defined with its signature line. It does not return a value, but square by reference is expecting that a reference to an integer be sent to it with and assigned to the variable ref. Remember, the number ref is going to be an alias then to the variable that was passed to it. And in the called environment, square by reference is passing a value. Square by reference is passing a value to the square by reference function. So number ref is a reference to the value that was passed to it, and the value that was passed to it in that calling environment will be changed and modified with every assignment to number ref within this function. So square by reference multiplies numRef by itself and stores the result in the variable to which numRef refers to in the caller environment, which means that we are modifying the original value in the calling environment. Pointer variables contain a memory address as its value. Now this is very important to understand. A pointer contains and stores a memory address. So it's not really storing an integer value or a double value. The pointer variable itself stores a memory address. A pointer contains the memory address of a variable that, in turn, contains a specific value. In this sense, a variable name directly references a value. So we could have C is equal to 5. C is the variable name, and it has a value of 5. And a pointer indirectly references a value. Dynamics typically represent a pointer as an arrow from the variable to that it contains as an address to the variable contained at that address in memory location. So if we have defined a count pointer, typically we have that pointing to, and we have our variable count, which is storing an integer value of 7. Count is declared as an integer variable name, and it's been assigned a value of 7. Count directly refers to a variable. In this case, it contains 7. The pointer by the name of count pointer stores a memory address that points to that integer, and it indirectly references a variable that contains the value 7. So indirectly, although this is a memory address that's being stored, it's the memory address that count directly refers to as the integer value 7. Declaring pointers on page 341. Pointers must be declared before they can be used. A declaration statement, int star, count pointer, count. I said star, that is your asterisk symbol, space, count, pointer, comma, count. So this is our declaration statement. The statement declares the variable count pointer to be of an integer pointer. That is, count pointer is a pointer to an int. And count pointer is read right to left. So we read right to left. So right to left, count pointer is a pointer to an int, an integer. So this asterisk operator is associating right to left. So count pointer is a pointer to an int. But count is a variable name, and it's declared to be of type int, but it is not a pointer variable. So in our declaration statement, count pointer is a pointer to an int, comma, but count is an integer variable name. It's going to be storing an integer. Now, the star or the asterisk in the declaration statement applies only to the first variable in the list. Each variable being declared as a pointer variable must be preceded by the asterisk. So if we had additional, we need to include the asterisk again. So from right to left, we know that count pointer is a variable being declared to be a pointer to an int, although count is simply a variable storing an int value. When an asterisk appears in a declaration, it is not an operation of multiplication. Rather, it indicates that the variable being declared is a pointer to this data type. The asterisk is a unary operator and associates right to left. On page 345. On page 345 at the top, we have our operators associating right to left, the unary operator, and we see our address operator and the star or the asterisk operator. And I was going to point out on page 345 that these operators operate as a unary operator. They operate on one operand, and they associate right to left. As I move down the operator list, we see that here's multiplication, division, and the modulus operator. Multiplication operates left to right, and it's multiplicative in type operations, but it is a binary operator. It takes two operands, 3 times something, 3 times. It's a binary operator, so multiplication 3 times 4, and we can get something done. So the asterisk or the star is a unary operator. It operates on a single operand, and it associates right to left. So once again, here's your operand. It's your variable name count pointer, and the asterisk is operating from right to left, indicating that this count pointer is going to be a pointer variable pointing to an int. Pointers can be declared to point to objects of any data type. So that could be integer, double, float, an account object. It is suggested to use PTR in each variable name to make it clear that the variable is a pointer. So in our example, we have count PTR. We might choose other names like number PTR as a variable name for a pointer. We might choose a PTR as a number name, another name for a pointer variable. The PTR is just a naming scheme that helps us as we're reading our code and helps remind us that this variable is meant to be a pointer. Initializing pointers, page 342. Pointers should be initialized to null pointer. Null pointer. Null pointer, or they should be initialized to a memory address, either when they are declared or in an assignment statement. A pointer with the value null pointer points to nothing and is known as the null pointer. Always initialize all pointers to prevent pointing to unknown or uninitialized areas in memory. If a pointer is accidentally pointing to a memory address that's storing something that we want to use within our program, we could accidentally overwrite existing memory. So we want to be very careful with pointers, and you and I are in charge of making sure that our pointers are always initialized to prevent their pointing to some unknown or somebody already assigned memory values, memory locations currently storing some values that are meant to be used in our program execution. Pointer operators. Page 342, pointer operators. The unary operators we have our and symbol, and we have the asterisk symbol, are used to create pointer values and to dereference pointers. The address operator so our operator is the ampersand. The ampersand address operator is a unary operator that obtains the memory address of its operand. So we might have a statement like int y. So y is a variable. It's going to be storing an int. We're going to initialize it to 5. So we are declaring and initializing y. Next statement, int asterisk y ptr, and we're going to initialize it to null pointer. Okay, I have from right to left, y pointer is going to be declared to be a pointer to an int. So I'm declaring a pointer. My pointer variable name is y pointer, and I initialized it to null pointer. Now the statement y ptr equals the address of y. This is the address operator. It associates from right to left. So y, we're looking for its address. So the address of y is assigned to ptr, yptr. And remember, pointers store memory addresses. So yptr is expecting that a memory address is going to be assigned to it. I'm assigning the address of y to the pointer yptr. The use of the ampersand or the address operator in the preceding statement is not the same as its use in a reference variable declaration from Chapter 6. Remember, in our review and in study in Chapter 6, the reference is the reference variable declaration. It's always preceded by a data type, as in int, ampersand, number ref, and that example is line 33 in figure 6.17. This ampersand is following the data type, so number ref is a reference to an integer, and it's actually the alias to the sending argument. When declaring a reference, the ampersand is part of the type. Okay, so here's our data type. The ampersand is part of the data type. In an expression like the address of y, the ampersand is the address operator, and it returns the address of y. In this example, it's the address operator, and we're looking for the address of y, so it's going to return the address where y is located in current memory. Statement. Y pointer equals ampersand on y assigns the address of y to pointer y PTR. I'm looking at figure 8.2 on page 343. And in the picture we have again y PTR, and we tend to represent that with an arrowhead. Y PTR is a pointer, and I've assigned it the address of y, and y is currently storing an integer value of 5. So now y pointer is pointing to the address where the integer value 5 is located in current memory. So we have a graphical view of pointer pointing to a variable in memory. So y pointer has been declared to be a pointer pointing to an integer value. The address stored at y pointer is the address of where y is storing the integer value 5. Now we have a representation graphically of y and y pointer in memory. So y pointer is defined to be a pointer storing an address which points to a memory location of an integer stored in the variable named y. Now the location of y pointer in memory is, for example, 500,000. So the memory location is 500,000 where y pointer resides in current memory. The memory location where y is stored is 600,000. So the integer variable stored in the integer variable name y of 5 is stored in the memory location 600,000. And the y pointer has been declared to be a pointer, it must store a memory address, and that memory address is pointing to 600,000. The actual address of Y pointer, as it's stored in current memory, is at the location 500,000. All right, back at our Unit 8 at D2L, I have published a definition of L values and R values. So if you would like to print that, or at least be sure to read through that information, probably something you already know from math classes and so on, but just to review as we begin to make use of the definitions L values and R values. In C++, every expression is either an L value or an R value. An L value returns to an object that persists beyond a single expression. You can think of an L value as an object that has a name, all variables, including constant variables, are L values, and R value is a temporary value that does not persist beyond the expression itself that it's used in. To better understand the difference between L values and R values, consider the following example. We have int main, int x equals 3 plus 4. In this example, x is an L value. It persists beyond the expression itself that defines it. The expression 3 plus 4 is an R value because it does evaluate, temporarily has a value, but that value does not persist beyond the expression itself. The indirection operator on page 343. The indirection operator, sometimes, probably most frequently called the dereferencing operator. Just know that kind of new terminology is making use of indirection operator. Dereferencing operator is more familiar to me. And if we think about it, a variable as a pointer stores a memory address. We're not really so concerned about that memory address of the pointer itself, where the pointer is stored. We're concerned about the memory address that the pointer stores because it is pointing to a value, a data type, an object that we want to maintain or access or modify. The indirection operator allows us to dereference a pointer. The unary operator, the asterisk or star, returns an L value representing the object, might be an integer, might be a double, might be a class object, to which our pointer points. The asterisk again associates right to left. So a statement out asterisk y pointer asterisk y pointer. Y pointer, we have a memory address stored at y pointer, but we want to dereference it. We want the indirection operator to return the value pointed to by y pointer. So we're dereferencing y pointer, the memory address that it's storing. We're not really interested in that value. We're interested in the value pointed to at the memory location. So we're going to dereference y pointer. That will return and print out the value pointed to by y pointer, which is 5 in our kind of ongoing example. So our output display is going to display the value 5. The statement asterisk y pointer equals 9. Well, this is our dereferencing operator again. Y pointer is being dereferenced, so we're looking for the value stored at the location pointed to by y pointer. And that value was 5. We're going to be overwriting it now with 9. So the value pointed to by y pointer is going to be reassigned 9. So our next statement, C in we can use pointers for input value assignments as well. So here we have y pointer dereferenced, so it's the value pointed to by y pointer is going to be reassigned with the input value. So it places the input value, whatever that might be, from the user in y, which is pointing to an int. It currently is 9. It'll be overwritten with the input value. So it is reassigned the input value. Using the address and the indirection or the dereferencing operator, we'll look at program figure 08-4. On page 344. Now this program demonstrates the ampersand or our address operator, and I just kind of try to think about that as the address operator, the ampersand. A ampersand, A address operator. So the ampersand is our address operator, and the star is our dereferencing operator. And those are our pointer operations. Memory addresses are output in this example, and they'll be output in hexadecimal base 16 integers, and of course will be platform dependent, so the output you get may vary from the output that's compared to on this program. So our program code, we have a pound sign include IO stream, and we're using the directives. We have our int begin end main. We have A assigned a value of, initialized to a value of 7 as an integer. It is a local variable to main, and we're declaring and initializing a pointer by the name of a pointer, and a pointer is pointing to an int it's going to point to an integer. A pointer is storing an address, so we are assigning the address of a to it. So it's going to be pointing to whatever a's value is as an integer. We ask for the address of a to be output. Well, that'd be our address operator of a, and that will be a's memory location, whatever that is in memory. We're going to ask that the value of a pointer is output. A pointer is a pointer, and it's storing an address. The value of a is, of course, the integer value 7 currently, and the value of what's pointed to by a pointer as a dereferencing operator. We don't want the address that's stored at a pointer. We want the value of the object pointed to by a pointer. That should print out the dereferencing operator of a pointer. So the address that it's pointing to, and we want to know that object, and the object value is integer 7. Let's see what happens. Sorry, I don't have Visual C++ up and started for you. We'll get that going here with an open project. I guess I don't have that for you yet, so let's just go ahead and check what the output is. The first is the address of A. Well, the address of A is going to be address representative for hexadecimal. So we're looking at the hexadecimal location. It's a memory address and platform dependent, so may agree with you or not, depending on the device and the operating system you're using. So the address of A is, okay, right there. The value of a pointer, remember a pointer is storing an address, pointers store memory address, and it should be pointing to A. So it's pointing to the same memory address as A when it was assigned and initialized. So those two memory addresses should be the same. The value of A is, well, A is an integer initialized to 7, so A's value is 7. And the value of a pointer dereferenced, we're looking for the star a pointer. We want to know the value that a pointer is pointing to. And a pointer is a pointer to data type int. So dereference a pointer. A pointer is pointing to an integer value. What is that integer value? It is 7. Now we know of the 3 ways in C++ to pass arguments to a function. We can pass by value, pass by reference with a reference variable, and that was discussed in Chapter 6, and now pass by reference with a pointer. Both pass by reference and passing by pointers enable programs to pass large objects of data to a function without actually implementing a copy, which expands overhead cost. Both pass by value and pointers allow for the modification of variables in the caller environment, because we are working with the pass by reference alias to the variable that was passed, or we're working with a pointer that points to the address of the memory location of the argument that was sent. Next, we look at figure 8.6 on page 346. This is a pass-by value used to cube a variable's value. Remember, pass-by value, we're passing a copy of the original variable to the called environment. Our function prototype, we're going to return an integer. Cube by value is the name of the function, and it is expecting an integer to be passed to it. Int main, begin end. Int number is a local variable initialized to 5. We're going to output the original value of the number is in a number's value, which is 5. Number is going to be reassigned to cube by value, and we're going to pass number to it. So I'm using my function call stack. I've called main. Main has been initialized with a local variable number to 5, and now I'm calling cube by value, and I'm passing number to it. I'm stacking cube by value. It's going to return an integer. It expects an integer, and n is a local variable. It's being passed the value 5. I'm going to return 5 times 5 times 5, which is 125. Return it as an integer to the calling environment, which is call by value number. We're returning 125, so this returns 125. It's assigned to number, so number is reassigned to 125. And in line 13, the value of number is, the new value of number is, well, the new value of number is 125. We exit main and we're done. So we return to main, main is done, we return and we're done with the program. This is an example of passing by value, passing a copy to the calling environment. Figure 8_7 on page 346 and 347. Pass by reference with a point argument. Void cube by reference is expecting an integer pointer as its prototype in line 7. A function receives an address as an argument, and if a function is receiving an address as an argument, it must define a pointer or parameter to accept the passed address. The header for the function cube by reference in line 18 specifies that cube by reference receives the address of an integer variable. So in line 18, our cube by reference header, we have an n pointer. It's being declared to be a pointer to an integer. N pointer, it must be a pointer parameter to accept the passed address, because in line 15 we are passing the address of number, not the value stored at number. We're passing the address of number. So you have to have a pointer in the function parameter list to accept an address. Then in cube by reference, we're dereferencing n pointer. N pointer, the value pointed to by we execute a main with a local value of 5. We're going to call cube by reference in line 13, sending a memory address, line 13. So we're calling cube by reference, stacks our memory stack. Remember that n pointer is pointing to the address of number that was passed to it. And then executing in the function, we have the value pointed to by n pointer, which is 5, times the value pointed to by n pointer, which is 5, times the value pointed to by n pointer, which is 5. 5 times 5 times 5 is 125. N pointer is reassigned then. The value pointed to by n pointer is reassigned to 125. We're done with cube by reference. Remove from the stack. We return to the calling environment. Cube by reference has reassigned number from the calling environment to 125. And we output the new value of number is. Number's value is 125. We're at the end of main, so we return to main and exit. I would suggest that both figure 8.6 and figure 8_7, the CPP programs, they're shared data files, so go ahead and set up your project and run and execute. Very interesting, very exciting. We're now learning information that only those of you that take advanced study will study and understand. We really do take a lot for granted when we're typing a Word research paper and making use of Word, or making use of our applications, or making use of our programming our Android phones. There's a lot of operating level control that has to take place, and we are now beginning to scratch the surface of memory and memory locations and dereferencing a memory location to getting the value that's stored at that memory location, and so on. As we're dissecting this program, the function protocol is defined in line 7, void cube by reference, passing an integer pointer. The compiler needs to know that information before cube by reference is called. So in the prototype, that statement declares a function with its name, the return type, if any, and the types of parameters. In this case, we are going to be expecting a pointer parameter, that is address, to be passed to cube by reference. All right, thank you very much. As always, return to D2L. We're working in Chapter 8, so the Chapter 8 unit lesson plan. All your homework and projects, tests, and due dates are listed there. And thank you very much.